Hi, this is Ariel Martinez, and this is my Lab2 motion of a falling object. I'll have a small introduction to the lab. I'll describe my lab procedure, my data, how I track my data with Tracker, and then I'll describe my models that I created using GlowScript for a model with drag and a model without drag, and then I'll compare and contrast my observations versus the two models, and then I'll describe what it means, what my data means, and some potential what ifs. For this lab, we looked at the motion of a falling object that was dropped from rest, and this object will have a net force because it is falling. As it is falling, it is affected both by gravity and drag, so therefore it will have a non-constant net force. In accordance with Newton's second law and the momentum principle, an object with a net force present will not have constant velocity, like I just explained. So therefore, we're going to need to use the velocity update formula, which is shown here as v final equals v initial plus f net divided by mass times delta t, and as well as the position update formula in order to graph with our models and the change in moment in position through time. So the formula for this is the final position is equal to the initial position and plus v average times delta t. And with a constant force, v average, it would just be the initial velocity plus the final velocity divided by 2. Whereas with a non-constant force, v average would just be predicted using v final. And what we're going to see with our models, we're just going to use v final for v average. And we're going to plot the data of the observed motion and compare it to the model of the data generated from the observations in initial conditions. One model incorporating gravity and one model incorporating both gravity and drag. So the procedure for the lab, I recorded a video of me with a still camera dropping a bag of flour from rest to the floor. Then I analyzed the motion of this object with Tracker and plotted position versus time. And then I used the initial position of this motion to create both of my models, one with drag, one without drag. And then I compared both the two models with the observed data. And so here's some of my observed data. This is a picture of me dropping a bag of flour and the time versus position and data points. So the mass of the bag of flour was 0.11 kilograms. That should be kg, not km. And so at time t equals 0, the initial position was almost 0, and negative 1.26 times 10 to the negative 2 meters. And then after the first time step, and just as an example, after the first time step of 0.33 seconds, the position changed to negative 4.098 times 10 to the negative 2 meters. And the initial velocity since the object was dropped from rest is 0. And just the time of last observation was 0.5 seconds. And this is my graph created using Tracker of position and versus time. So we can see that this graph has a negative slope. And since it has a concavity, it means the velocity was not constant because there was force present. And now we're going to switch over to my models, which were created using the initial conditions of the observations. We have here at the top left, we have the initial conditions, and then we have the while loop, which will iteratively graph points in the graph of the position as time goes on. And here we have the graph of this model. This model used only gravity, so there was no drag incorporated. And then this other model uses both gravity and drag, so we can see in the net force we include both the mass times gravity, which is the force of gravity, and then we also include the drag force in the y component, which the previous model, as you can see, did not include that. It only included the force of gravity. And so we have the code and the graph. And now we're going to compare the observations versus both models. Here the observations are the dotted points. The orange line is the model with no drag, and the gray line is the model with drag. As we can see, the model without drag is more accurate because I believe because the shape of the bag of flour that I used, it does not allow for much air resistance, so the drag constant should be very small to non-existent. So therefore, the model with drag would underpredict the motion because it would make the downward force smaller. So what does this all mean? So my final velocity for the model without drag was bigger than my final velocity than my model with drag, and this is because the model without drag had a larger downward net force and therefore reached a larger final velocity. So from this we can see that the model with drag predicts a terminal velocity, which the model without drag, the model that only shows gravity, does not. Because as velocity increases, as the bag of flour drops, drag, which is proportional to velocity, also increases to the point where eventually it'll equal the downward force of gravity, and then that force will become 0. So velocity becomes constant, and that would be the terminal velocity, which the model without drag does not reflect. So now as a what if. So what if the bag of flour would have been dropped? It would have been thrown down rather than dropped. So therefore it would have had an initial velocity. So because it still experiences a drag force, the object would still reach a terminal velocity, which would actually be the same as the object that that was just started from rest. And here at the bottom right, I have a graph of the same model as the model with drag, but now instead of with zero initial velocity, with a velocity of negative 0.85 meters per second. And we see that even though it traveled the larger distance in the same amount of time, that was because it started with a larger velocity, so in the same amount of time it traveled further. But despite that, they both had roughly the same final velocity of negative 4 meters per second, which would be the terminal velocity for both models.